to talk about today is just part of the work that we've been doing, and it's work that's been funded by Institute of Fertilisers and GRDC and the Department of Forestry and Fisheries. So looking at a number of different products, and today I'm just going to talk about this one product, which was a project funded over the last 3 years. And I was working on this with Billy Chen at the University of Melbourne as well, and also with student Canera. We work closely with Charlie Walker and Aaron Davies at the Institute. So I was asked to give take-home messages first. So for those of you that just want to stay for a couple of minutes, you can read the first couple of slides if you don't want all the details. So, from measurements that have been done around the place, we know that ammonia loss from the surface supply degree can be high, and it occurs pretty rapidly once the urea is in the system. So depending on whether that's a fertiliser or from the urea as well. And from the work that people have done, where we've done work with other people as well, it's shown that these products known as urease inhibitors can slow the conversion of urea to ammonia. That's what they're designed to do. And in the process of doing that, they can reduce ammonia losses. And they also slow down, by slowing down the rate of ammonium production from urea, there's the potential for them to be used for seed safety in terms of reducing that ammonium toxicity. So they can provide real economic savings in particular situations, and that would depend on whether you can reduce your nitrogen inputs, because all these products that have additional compounds on them are obviously sold at premium prices. And there's a dependence on climate conditions as to what economic benefits will occur. So the greatest benefit that we've identified is when you put surface applications of urea out, and where there's potential for high loss systems. And I'm going to talk obviously a lot about this through the presentation, but those systems that we've identified are high organic matter systems, or systems where you have high pH occurring. And where there's limited water, so you haven't got irrigation to wash the urea in, or you're not, you want to reduce the risk associated with waiting for rain to come immediately after you fertilise the application. So yeah, they're designed a little bit to improve the logistics of managing your fertiliser and watering systems if you're using an irrigation system, or your reliance on rainfall occurring immediately after application. So just to give you a bit of a background as to why I'm actually standing here, as Rob mentioned before, what we're looking at the university is all these different products that could potentially lead to reductions in losses, and that's losses of nitrates and gaseous emission losses as well. And the overall theme of what I'm looking at is trying to reduce what you actually put into the system by reducing those losses, so without having a cost of reduced production. And we're studying this looking at lab studies where we can, under controlled conditions, we can look at the interaction between these products, different soils, moisture and temperature conditions, so that we can see in detail what's happening there. We use various studies using isotope labelled fertiliser products, and they're quite involved studies, but of course because they're in the lab, people question the validity of those in terms of real life situations. So we also do field studies where we're sort of testing what we've measured in the field, in the lab. Okay, so now getting into the background of why I've come up with those take-home messages. So if you put urea onto the soil and there's a little bit of moisture around, you get conversion of urea to ammonium or ammonia, and this process is called urea hydrolysis. And it's catalysed by this enzyme called urease, and urease is an enzyme that's found in anything organic, so it'll be in the plant material, in manures that are in the system, in soil, any organic material has it. You get this process called urea hydrolysis that leads to the formation of these ammonia compounds, and that then leads on to subsequent steps of the nitrogen cycle, which I'm not going to talk about. So this ammonia can go off as a gas, and whether it goes off as a gas is driven by a number of factors related to the surface topography of your site, what sort of crop you've got there, and soil factors like pH and how much water's in the system. Whether you get ammonium or ammonia is pH dependent, and so when you've got an alkaline system, you get a drive towards ammonia production over ammonium, and that's the one that goes off as the gas. So in solution, there's this distribution that you have of ammonia or ammonium based on pH, which you can relate to situations that occur in the field. And so as you've got alkaline conditions, so up to a pH of about 7.3, you don't get very much ammonia in the system, and most of that form is in ammonium form. As the pH increases, ammonia becomes the dominant form that occurs until you get all ammonia and no ammonium being produced. And the point in solution where you consider to get about 50-50 of those two compounds is about pH of 9.3. So in the field, if you've got an alkaline soil, you're at a risk of ammonia loss already. But it's not just the soil factors. If you put urea onto acidic soil, you can still get ammonia loss, because as the urea granule hydrolyses, you get this localised hotspot of pH around that hydrolysing granule, and that can drive ammonia volatilisation. And that's what this diagram here is depicting, is the distance from the centre of the, I can't see the pointer on that, I just can. The distance from the centre of the urea granule and the differences in pH. So if you had really quite rapid hydrolysis of a granule of urea, you can get this very localised elevated pH that drives ammonia loss. So this loss can be quite high, and in some situations they've measured as high as 57% of applied nitrogen goes off as ammonia. So it can have an economic impact if it's that high. It can have an environmental impact as well, because the ammonia that goes up is actually redeposited, and then it goes through the nitrogen cycle at that other site. So if you think about, say, a feedlot that has a high amount of ammonia coming off, being next to a native ecosystem, that can cause quite dramatic changes. And ammonia in the environment can also affect health. Okay, so how much ammonia is lost in Australia? This is a bit of a daunting table, I'm sorry. So I've just gone through the literature that's been published on ammonia loss in Australian agricultural systems. And what I want to sort of get from this is there's been a number of studies in different climate types on different crops and across different seasons. And the rates of application in many of those systems are quite high. And the percentages of loss that have been measured, whilst they differ across all those across those different experiments, we're getting some general ideas about what you might expect from different situations. And I've tried to come up with an amount of dollars per hectare that you're actually losing from these sites. So in terms of what you're probably interested in here, it's mostly the work that was done by a colleague, Deb Turner, where she measured ammonia loss from urea, ammonium sulphate, and from UAN. And she measured loss from all those different fertilisers at this cropping site over in Western Victoria. So this is around Longrenong and Walpia. And she measured losses of up to 16% of the applied nitrogen. In the studies that I'm going to talk about today is related more to a pasture site, because it was a pasture seed crop. And in pastures, in previous studies that Richard Eckart's been involved in up in northern Victoria, they measured about 29% loss of nitrogen. So what seems to be coming out of all these studies is that we're getting very high losses from pasture systems because they're very organic, and lower losses in cropping systems related to a number of factors, including the organic matter and the timing of your fertiliser application and the crop, the form of the crop. Okay, so coming to the urease inhibitor, so this is the process of urea hydrolysis, and the urease inhibitor just slows down, doesn't stop, it slows down that process of hydrolysis by the actual inhibitor blocks the active site on the urease enzyme. So instead of the urease working on the urea, it works on the inhibitor. So that process occurs for a certain amount of time and just slows down the rate of urea hydrolysis. After a set amount of time, then the effect of the inhibitor is essentially gone. So you've probably heard of products Green Urea 7 and Green Urea 14 that are designed to slow down urea hydrolysis for 7 and 14 days. Okay, and I'd like to point out that I'm aware that the urease inhibitors are only just one of the many management options that are available for reducing ammonia loss. I'm not saying that this is a product that's, this is the only way you can address this issue. There are other ways, and they can apply or not to your farm management. So deep placement's an option, but in pasture systems that we look at, that's not really feasible. Watering in, once the urea goes into the soil, then there's no risk of ammonia volatilisation because it can't actually volatilise from below the soil. So if you've got irrigation or rain that you can count on, then they're not going to add that much benefit. And if you use a form of fertiliser that's not urea, then obviously a urease inhibitor has no role. Now I want to just look at some of the lab work that we've looked at first, and I've presenting data from 2 typical types of soil to show you the differences that we've seen in different industries. So this is from a pasture soil collected down from Birregurra in Western Victoria. And it was an acid soil, it had a lot of clay and a high organic matter content, and the urease activity was very high on this soil, and that's the amount of urea that's converted from urea to ammonium per unit time. So the data that's shown there is the urea hydrolysis of straight urea granule at these 3 different temperatures. So by 2 days, no matter what the temperature, it had all gone in these incubation studies in a lab. When we added the inhibitor, so at 15 degrees, the inhibitor, you can see here, has reduced the rate of urea hydrolysis. So at 2 days, we've still got about 50% of the urea remaining. When you increase the temperature to 25 degrees, the inhibitor is not working as well because it's breaking down a bit quicker. So we still get inhibition of urea hydrolysis, but it's slowed a little bit. So we've only got 30% of the urea remaining. And at 35 degrees, again, the impact is less. So at 35 degrees, there's minimal effect of the inhibitor on this particular soil type. Now, this is another soil type. This is from Walpia. And it's an alkaline soil. It's got much lower organic carbon, and the urease activity is much lower because there's less organic matter in the system, there's less urease. So you can see here the slope of the urea hydrolysis at 15 degrees is much less than it was in the previous slide. And then we've got urea hydrolysis at 25 and 35 degrees. And then when we add on the inhibitors, at 15 degrees, the inhibitor's working really well. So after 12 days, we've got about 60% of the urea left in that soil. At 25 degrees, it doesn't work so well. And at 35 degrees, it doesn't work so well, but it's still working well for this particular soil. So the next slide's just summarising those two charts showing the differences in those 2 systems. So the one on the left, the clay loam, is what we're typically seeing in pasture soils, and the one on the right is what we've typically seen in cropping soils, but those lines do move around a little bit depending on the particular soil properties. So that's for these particular soils there. So in terms of looking at industry differences, I guess you're mostly concerned about grains here, but if you had pastures in your system as well, then you'd be interested to know that in terms of retention of urea in the soil, seeing that in the pasture systems there's rapid urea hydrolysis, it's much slower in the cropping systems. Temperature has an effect in both systems, but sort of less in the pasture system. When you put the inhibitor on, it does slow the urea hydrolysis in the pasture to some extent, but much more in the cropping system. And temperature is important. So in terms of retention of urea, we'd say that in the cropping system, the urease inhibitor is working much better at retaining urea in urea form. And that's because of that low organic matter content. But ammonia is a different thing. So ammonia volatilisation comes about through that rapid hydrolysis of urea driving ammonia loss. And so I'm going to talk now about a field experiment that we did in Maroon in southwest Victoria, which was on a ryegrass seed crop. And we used these passive ammonia samplers, these little things here, to measure ammonia loss. Now, I've just got some figures here of different types of whiz-bang machines that you can use to measure ammonia loss. That's Deb there using a laser to measure ammonia loss. These are analyzers that we use for measuring different gases. There's different ways of measuring single heights or multiple heights. And that's an FTIR that can measure multiple gases off a single site. And this ammonia laser that we've just purchased that we're going to be using soon. So this is the field site where we measured, and the first thing I wanted to point out that this is the size of the circle that we work on. A 50-metre diameter circle is what we use for our treatment area. So you need very large areas to get a realistic measure of ammonia because it gets blown around. So just to compare that, that was our small plot trial there that had 100 small plots in it. So it's quite hard to find an area where you can, well, in pastures in particular, where you can do these experiments. In cropping it's probably not because you've got bigger areas to work with. So in this field experiment we did measurements in autumn and spring. It was pasture acidic again, 2.5% organic carbon. And in our autumn trial we measured, this is our flux of ammonia loss, and what I want to point out here is the speed at which that ammonia came off. So within 4 days that flux had come through. And after that, there was essentially none. We ran the experiment for 28 days and measured over that time. The other thing to look at is that the use of the inhibitors essentially got rid of that flux that occurred in those early days. So this flux here is coming about because the applied urea granules have rapidly hydrolysed in that high organic system, and that's driven off the ammonia gas. This was perfect conditions for ammonia loss. We had a little bit of dew on the ground every morning and light winds that blew the ammonia away. So that enhances the ammonia coming off. When we look at the cumulative loss, over that time we get this very sharp peak here of ammonia loss coming off. And what we found in autumn was that we got, of the applied urea, 30% of it came off as in those first 2 days as ammonia. When we put this inhibitor on, we reduced that down to 10% of the applied nitrogen was being lost. We also ran the experiment in spring, and we got these much lower numbers. 2% of the ammonia, of the nitrogen came off as ammonia in spring, and 1% with the inhibitor. And the reason it was so low in spring was because it was wet, the site was already wet, and it rained essentially as we were finishing up the experiment and that night. So we didn't have a lot of rain, for about 4 millimetres, but it was just enough in addition to that wet site to prevent that ammonia coming off. So this result sort of highlights the fact that these products are useful for particular situations. Now this is the work that done on the wheat crop. And you can see here the slope of that line is much less steep. So the ammonia is coming off over about 16 days in the cropping system. And that's because the rate of the urea hydrolysis is much slower in that system. So the loss from that wheat crop was about 9.5% with the urea, and it dropped to about 1% when the inhibitor was applied. And those two soils, again, differed in a number of different factors, including levels of organic matter. Now, with that pasture trial, we looked at, well, we've lost 30% with urea, so we'd expect to get a biomass production benefit from that because we've got all this additional nitrogen in the system. But as you can see, we haven't. So in autumn, we've got the biomass produced. It increased with the addition of the fertiliser, but there was no difference between having the green urea and not having the green urea. And the agronomic efficiency and the nitrogen uptake were all pretty similar. In spring, we got much higher production due to just the climatic conditions and the production potential in that region at that time of year. But again, there's no difference between the two fertiliser treatments in terms of agronomic efficiency. And so what we think happens here is that there's just too much nitrogen in that system already. So a lot of these sort of preliminary experiments, you run an experiment with fertiliser and then fertiliser plus something that loses it. If you're going on industry standards that are putting on an amount that's used, that's probably going to have sufficient nitrogen in the system even if you lose what goes off as the gas. So what we did, what we had going at the site as well was this 15N microplot study. This is a labelled isotope of nitrogen that you can trace and measure, and it shows you, if you put it onto the soil, it goes into the soil and then it gets taken up by the plant. So it's a way of working out, of the nitrogen that you put on, where is it going? Is it going into the soil? Is it being leached? Is it being lost? Or is it going into the plant? And this is where we found that it went. So of the percentage of the nitrogen that was applied, we found that just under 30% went to the plant, just over about 12% went to the root. We had about 24% in that top part of the soil, and then a little bit went down further, but we didn't get any at great depth, so that's a good sign it wasn't leaching from the system. So in the plant, we'd had about 42% of the nitrogen that was applied was taken up by the plant from that particular fertilisation event. Surprisingly, the actual measured loss was the same as what we'd measured in the ammonia experiment, which was pretty exciting and a real result, because you know those things, the numbers were so close we kept looking at them thinking, can this be right? But what we found was when we looked at how much nitrogen was actually taken up by the plant, the total nitrogen taken up versus how much came from the fertiliser and how much came from elsewhere, we found that the plant was taking up, say, 64 kilograms of nitrogen, but from the fertiliser, based on those 15N studies, we thought it was 19 kilograms, which is only about 30% of what the total plant uptake was. So the rest came from the soil. So what that meant was there was enough N in the system already that saving that amount from the use of the inhibitor didn't actually make any difference in this situation. So just to look at an application on farm, I've just run the numbers through for this particular site. I said if we're putting 40 kilograms of nitrogen on per hectare, came up with a value of $57 per hectare to put on the urea. Saving that, losing that amount, you lose about $17 per hectare. If you can put on 28 kilograms of nitrogen, where we got maintained productivity, if you use a urease inhibitor and drop the rate to 28, because you know we can get the correct production of that system, you've got to pay a premium of $50 per tonne for the inhibitor product, but it still came out at about $42 per hectare, so it's cheaper to use the inhibitor product at a lower rate than it would be to put on the urea and lose that bit that you've lost. In cropping systems where the losses come down, the difference in that margin gets tighter, but even down to about 10%, you know, you're still making a little bit of a benefit from paying more for the product. Just to look at the risks, the environmental risks, there aren't really any, except that if you save all that nitrogen and don't reduce your inputs, it's potentially going to be lost elsewhere because it gets into the nitrogen cycle, so it could be leached or go off as nitrous oxide gas. The economic risks are you've got to pay a bit more for the product, but hopefully that's balanced by reductions in the amount you actually have to put out. And there don't seem to be any negative long-term impacts of the inhibitor on the soil biology or any contamination of the environment issues. So can a urease inhibitor reduce ammonia loss? So my answer was yes, it could, but you need to consider the soils that you're working on and how organic they are, what the pH is and what the risk is there, and what the impact of the inhibitor will be. So it will work in some seasons, but it won't work in other seasons depending on the temperatures. The benefits are that you've got this increased flexibility in operation of the farm if you're waiting to do fertiliser and watering at the same time. And it's got economic benefits, but you need to think about when you're going to use it and how you can manage the nitrogen inputs to cover those additional costs. And this slide, I guess, is sort of my last slide, just to come up with the guidelines and recommendations of when you might advise people to use a urease inhibitor. So it's beneficial if you're using urea, but if you're using ammonium or nitrate-based fertilisers, it's not going to be beneficial. It's good if you're using granules. If you're using liquids, then the risk of ammonia loss is essentially gone. If you're subsurface applying the urea, then there's no benefit versus surface applications. And then looking at your ground cover, but that also is affected by your soil pH as well. And then essentially it comes down to the logistics, which cover all of those different aspects in terms of your rainfall, your irrigation, and your soils and your management of your crop cover and things like that. So thank you very much, and I'll take some questions if there's time.
Helen, you didn't make any mention of soil moisture at different times. Would you like to make a comment on that?
Yep, okay. So if you put your urea out when it's bone dry, that hydrolysis process isn't going to occur. If you put it out when there's moisture in the system, then that process occurs. If there's a little bit of moisture, you only need a little bit of moisture for that hydrolysis to occur. If there's a lot of moisture in the system and your urea sort of dissolves a bit, then that will reduce the risk of fertilisation a bit. Yeah. So in summer you might say, well, if you're not going to get any moisture, I guess you don't want fertiliser anyway.
But a heavy dew might be enough to start the process?
Yeah, a heavy dew will certainly drive it, and that's what we saw when we got those 30% losses. Yeah.
Just to further that one, if I get in a waterlogged environment where you're just trying to keep the crop alive, what are the dynamics of that, I guess?
Well, so in that spring study we did, the site was quite wet, and so the urea granule can actually dissolve a bit, and that once you get a dissolution of that, it spreads out that process of hydrolysis, so you don't get such a localised hotspot. So I guess the risk of getting such a high loss is removed a bit, but you could still get a bit. But yeah, I haven't really worked in super waterlogged conditions, but in rice they've still measured losses. Some of John Freeney's work, I think, measured ammonia loss from rice.
I suppose you'd have to question whether you put urea out in a waterlogged situation anyway, or wait till it dries up.
Yeah, well, I guess the situation in the southwest is often you're just trying to keep a crop alive through a short time or keep it productive anyhow. And urea is a way of doing it because nitrogen's